Now that we've talked about pressure and differences in pressure on a map and talked about pressure and height in the atmosphere, let's actually talk about why this even matters in terms of high pressure, low pressure, and what we all came here to talk about, wind. So for this goal, or for this lecture, our goals are first to understand what forces act on the wind. Then we're going to talk about an important model called the two-column model. I'm going to blitz through it, then I'm going to give you a quick TLDR summary of it. And then I want to talk a little bit about the pressure gradient force and how to calculate it. So first let's talk about the wind. So what is wind? Well, wind is simply air in motion. And because it's motion, we have to consider what are called Newton's laws of motion. And Newton has three of them. The first law is what's called the law of inertia. And the law of inertia states that an object in motion will stay in motion unless a force acts on it. So let's say you were in a place where there were no forces acting upon something, and then you threw it. Or you had like a ball or something and you threw it. The ball would continue traveling in the same direction. It would go straight as long as there are no forces acting upon the ball. Now this doesn't happen here on Earth because there are all kinds of different forces that'll act on that ball. Imagine if you're a pitcher playing for a major league team, like Madison Bumgarner, or I don't remember who else is very popular today. Let me go back to my day. Mariano Rivera or Jared Weaver, and you're pitching the ball. Well, eventually that ball is going to slow down and it's probably going to sink to the ground. Why? Because there's drag from the wind, there's drag from the air, there's gravity acting on the ball. Those things are going to change the ball's motion. However, supposing that no force acted on an object, it would just stay the course. It would continue traveling in the same direction as long as there's no net force acting on it. Now, with that said, going into Newton's second law says that the net force exerted on an object is equal to mass times acceleration. Now, I want to really stress here the idea of a net force. So, usually, there isn't just one force acting on an object. Like the good old Jared Weaver pitch I just talked about, as that ball is flying, there are numerous forces acting upon it. There's gravity pulling it down, there's drag from the air that's slowing it down, and there are even other forces that are acting upon it, and each of these forces adds up to produce an acceleration. So when we talk about the idea of a force, we're talking about the sum between individual forces. And then the third law, which we're not really going to use today, is what's called every action has equal but opposite reaction. And this law actually explains the idea of thrust. So let's say you have a rocket and it's flying up into the sky. Well, coming out of the bottom of that rocket is a huge downward thrust. And the force of that downward thrust also creates an upward motion. So, and this actually gets important when we talk about the idea of centripetal acceleration, centrifugal acceleration. We're not going to stress too much about that. But taking these three laws together and talking about the wind, here's what we need to know. Using Newton's laws, first we're going to assume that the mass of the atmosphere remains constant. And this isn't exactly true, but it's a good approximation, so we're going to use it. Forces acting on the wind will accelerate it. Forces acting on the air will accelerate it, creating wind. And when I say acceleration, I'm actually talking about one of three things. And these three things are either forward acceleration, reverse acceleration, or what's called deceleration, and then changes in direction. So forces that act on the wind will either speed the wind up, slow the wind down or change the wind's direction. So if you think about that ball that I was talking about, well, the two forces I talked about, the drag force, that slows the ball down, and then gravity's pulling the ball towards the ground, so that's changing the ball's direction. Well, forces that act on the wind do the same thing. So there are three main forces that we need to talk about to really understand what acts on the wind. And the three forces are the pressure gradient force. This accelerates the wind, this speeds the wind up. This is what we will be covering in this lecture. The Coriolis force, this changes the wind's direction. We'll talk about that in the next lecture. And then friction. Friction slows the wind down, and it also greatly affects the relationship between the pressure gradient and Coriolis force. We'll talk about those in the next lecture. But first, let's talk about the pressure gradient force. So let's suppose you have two areas of high pressure and low pressure. Well, the pressure gradient force is caused by the fact that Mother Nature hates imbalance. That is a key theme in nature, period. Mother Nature is always seeking to equalize everything. A natural system will tend to balance. Everything tries to balance each other out. So if you have a high pressure area, that location has more air above it. And then a low pressure area has less air above it. And so what happens is excess air from the high pressure will travel towards the low pressure until the two are equal. A good demonstration of this, if let's say I had two tanks of water and a hose connected between the two, and I fill one tank all the way up to the top and the other tank halfway. The tank that's full is high pressure. The tank that's only half full is low pressure. And what will happen is water from the full tank will actually then travel to the tank that is only half full. And so the net motion is from high pressure to low pressure. And this net motion will continue until the two have the same pressure, until the two have the same amount of water in the tanks. And so the pressure gradient force moves wind from high pressure to low pressure. And this is all caused by imbalance. So air moves from high pressure to low pressure in order to achieve pressure balance. High pressure to low pressure. And this is going to become important in a few minutes. Now, for us to understand how we even get this high pressure and this low pressure, we need to understand what's actually happening at the surface of the Earth. And in order for us to do this, we need to look at what's called a model of the atmosphere. Well, what is a model? Well, just this past weekend, as I was recording this, I purchased a model airplane. And a model airplane is simply a simplified representation, a simplification of a real-sized airplane. And a good example I have right here is you have a model Boeing 747 right next to a real-sized Boeing 747. Now think about a real-sized Boeing 747 and all the components that it has in it. All the different switches and buttons in the cockpit, all the different seats, all of the opening doors, the baggage doors, all the landing gear, the different engines, all the different components in that plane. It is a giant plane, and it's used for traveling passengers and equipment and stuff from one location to another. Now let's say I create a model of it. And let's say I don't need passengers to fly in the model. There's no cockpit, so I don't need instruments and stuff in the cockpit. Since I'm not loading any passengers or equipment into it, I don't need doors. I take away a lot of these different complex pieces to create a more simplified representation. That's what a model is. It takes a complex system, a large system, and it makes it much more simplified. And the purpose of this is the simplified model is easier to work with. I mean, if you take a look at this smaller Boeing 747, it's a lot easier to build, it's a lot cheaper, and it's a lot easier to work with. Meteorologists do the same thing with the atmosphere. We take an overly complex atmosphere with so many variables, so many moving parts, and we whittle it down to just the main things. We've actually seen models already in this class. We talked in the last module about this thing called an air parcel. And I said that air parcels behave adiabatically as they rise in the atmosphere. This means they cool only due to expansion. This is 99.9% true. Now, there are some things that happen that can influence the temperature of an air parcel, but those things are so minute and so complex that it really isn't worth the trouble to have them. It would make the model a lot harder to work with, it would be much more difficult, it would be a pain. So we get rid of those complexities, and what we have left is something that's a lot easier to work with. Well, we'll see more models as we progress through this quarter. In the next module, we're going to talk about what's called the three-celled model. Then we're going to be talking a lot more about forecasting models. So we'll see other models in this quarter. But for this lecture, we're going to talk about what's called an air column model. And an air column model is what we use to understand how air pressure changes. So how do we get high pressure and low pressure, and how do we get wind in the first place? Well, to understand this, let's look at an air column. So here's our air column right here. And as I said, because it's a model, we take away complexities. We simplify the model. And here's how we simplify this air column model. The first thing is that, unlike the real atmosphere, which behaves like that pyramid of cheerleaders, we actually don't have crowding near the surface. Rather, air is uniformly distributed in the column. The second thing is the column's width does not change with height. So again, just like the pyramid, we don't get that here. Instead, the column's width is straight up, and it doesn't change with height. It's a perfect rectangle. And then the last thing is air is not allowed to enter or leave the column on its own. So here we have this air column. It has a certain number of molecules in it, and let's assume that each one of these dots represented an air molecule. The air is uniformly spread out. The width doesn't change with height, and air doesn't enter or leave the column. Now, with that said, if we wanted to know what the surface pressure was of this column, we would look down here at the surface, and we would simply count the number of dots above us. Now, if we wanted to know the air pressure at any given elevation, we would just, at that elevation, actually I'll draw a line instead, at that elevation, we would just count the number of dots above us. So that would be our air pressure. So our surface pressure would be all of the dots. So that's the surface pressure. Let's undo that. That's okay. So that's the surface pressure, and then this is the pressure at this height. That's the pressure at that given height. So now let's do a few things with this air column model. Let's suppose we added air into the column. So now we have more dots. How would that change our surface pressure? Well, if you remember, surface pressure is the sum of all the dots. So if you count all the dots, that's surface pressure. If you add air into that column, you have increased the surface pressure. Why? You've added dots, so there's more dots. Let's suppose instead you ripped off the lid and you took some air out. That would mean less air, less dots, lower pressure. On the other hand, let's suppose that we heated the column up. Let's suppose we warm the column up. What does warm air do? Well, if you remember from a few modules ago, we talked about when air warms, it rises. And because air rises, that makes the column taller. Now I said that the width of the column can't change. I didn't say anything about the height. So if we have warm air in the column, it becomes taller. If we have cool air in the column, it sinks, it creates a shorter column. Now with that said, let's talk about a very crucial model of the atmosphere called the two-column model. We're going to use this a lot in the next two modules when we talk about cyclogenesis, when we talk about the three-celled model, when we talk about global circulation, when we talk about the jet stream, when we talk about sea breezes. All of those things come back to this model. So this is a fundamental model in meteorology. And here's how it works. Let's suppose we have two columns of air, and each one of them is identical. So they're identical. They have the same width, they have the same surface temperature, they have the same height, they have the same number of dots in them. Everything about them is the same. All right? One of them is located over city 1, the other one is located over city 2. All right? The pressure changes with height are the same. Everything about them is the same. Now, let's warm one column and cool the other column. So now let's do that. And as we do that, this is what we end up getting. So if we cool column 1 and warm column 2, column 1 shrinks, column 2 rises. Column 2 grows, column 2 becomes taller. Now at this point, we haven't added or removed any air from either column. We haven't done anything like that. So the surface pressures are still the same. The surface pressures are still the same. But let's actually go higher into the atmosphere. Let's go aloft. Aloft is just a fancy name for higher in the atmosphere. And let's look at these two black dots. They're each at the same elevation above City 1 and above City 2. But if you notice, what is the air pressure at that dot for City 1? What is the air pressure for the dot over City 2? Well, the way we can figure this out is by simply counting the dots. So here's that elevation over column 1, and we have 6, 12, 18. So the pressure over at this dot, at this elevation over City 1 is 18. Meanwhile, the pressure over here is 6, 12, 18, 24, 30, 36, 42, 48, 54, 60. It's 60. So what we end up getting is low pressure develops aloft over the cold column. High pressure aloft develops over the warm column. Why? Because at this height, this arbitrary height right here, we have more dots above us in the warm column than we do at the cold column. Now at this point, the surface pressures are still the same. Something's going to change that in a moment, and I'll talk about what that something is in a moment. But right now, we're just looking aloft at this arbitrary height. Now, let's suppose that we allow air to travel just between these two columns. So now we're adding a complexity to our model. We've made one change to it. We're now allowing air to travel. Well, based on the pressure gradient force, what we talked about earlier, air is going to travel from the area of high pressure to the area of low pressure. And this is again because Mother Nature hates imbalance. So air will travel from the higher pressure to the lower pressure. And it'll continue to do so until the two become equal. So air will go from here at the high pressure to over here at the low pressure. And it'll continue until the two are the same at that height again. Here's the problem though. You now have air escaping this column. That causes surface pressure to decline here. Why? Because now you have fewer dots here. You have air that's traveling away. So that causes surface pressure to lower. Meanwhile, over city 1, you now have dots being added. Air is being added to this column. That causes surface pressure to increase. And this all happens because of the pressure gradient force. Again, air is moving over here. Air is moving from the high pressure over city 2 to the low pressure over city 1. So now you are losing air over city 2 and you're gaining air over city 1. That creates high pressure at the surface over at city 1 and low pressure over the surface at city 2. So eventually what happens is by doing this, you've now created imbalance at the surface. You've created imbalance at the surface. So now what's going to happen is air is going to again move from the high pressure at the surface of column 1 to the low pressure at the surface of column 2. That's going to cause pressures aloft to again increase over city 2 and decrease over city 1. And what you end up getting is this never-ending atmospheric circulation. And the circulation will continue to happen until balance is achieved. And the only way balance is going to be achieved in this case is if both columns have the same temperature. Both columns have to have the same temperature. And believe it or not, this is one of the key forces in weather. We have two different locations heated up two different ways, so they have different temperatures, therefore they have different pressures, therefore wind blows between the two of them. And this is how we get weather. It all occurs due to uneven heating of the earth. That's so crazy to think about. Uneven heating of the earth creates wind. Well, here's the TLDR version of this, because there's a lot of stuff I just talked about. So this is just a summary of it. And it's summed up into 6 steps. So the first step, we have those two columns that are identical. Same height, same number of molecules, same surface pressure, everything about them's the same. Then we warm up one of the columns, and that column becomes taller. We cool the other column, and it becomes shorter. What actually happens is, in the warm column, high pressure aloft develops. That's high pressure high above the surface of the earth. Meanwhile, low pressure aloft develops over the cool column. So high pressure aloft over the warm column, low pressure aloft over the cool column. Well, since Mother Nature hates imbalance, air begins to travel aloft from the warm column to the cool column. This causes air to be escaping the warm column, therefore surface pressure decreases. And then air over the cool column is now getting higher since there's air molecules moving in, so surface pressure there increases. And then at the surface, air moves from the cool column to the warm column. And that is the two-column model. We actually see this in our everyday life. And in this week's module activity, you're going to take those steps from the two-column model and you're going to sum them up in the sea breeze. The sea breeze behaves the exact same way. And the reason why is because of what's called specific heat. Water has a specific heat 5 times as great as land. Therefore, water needs 5 times as much heat to warm up than land does. So during the daytime, land becomes really hot, whereas the ocean stays relatively cool. So now let's take our two columns, let's plop one over land and plop one over the ocean. The one over land is going to become very tall. Meanwhile, the one over the ocean is going to be relatively short. And so this creates high pressure aloft over land and low pressure aloft over the ocean. And wind then travels aloft from the land to the ocean. What that does is because air is escaping the column over land, that decreases the surface pressure over land. Meanwhile, since air is coming into the column over the ocean, that creates high pressure at the surface. And then finally, air at the surface starts at the ocean and travels over land, over to the land. And that is the sea breeze. Interestingly enough, at night, the opposite happens. At night, because land has such a low specific heat, it cools off really quickly. Whereas air over the ocean stays relatively the same temperature. So now you have a relatively warm air over the ocean and a relatively cool air over the land. So in this case, you've got a tall column over the ocean and a short column over land. So a relatively tall column over the ocean, relatively short column over land.